Okay, I believe everything should be in order. Let's get a copy of the solutions and the exam and continue. Same old, same old. Okay, those should be uploaded. Question 2 is where we're starting off. 4 rectangles of equal width are used to approximate the area under the quadratic. State the width of each of the rectangles. Well, that's pretty chill.
I was saying, is it 0.25?
0.25. Yep. 0.25. Perfectly fine. Decimals are allowed as long as they are closed form decimals. Cool. I'll just drop once again the exam solutions and the exam in the chat. So anyone else that joins should be able to see them now. Cool. Alright, that's A. Part B, find the total area of the 4 rectangles above. Reminder, this is tech active, although I guess it shouldn't be... it wouldn't be the end of the world to do this by hand, but it being a 1 marker, you probably wouldn't want to spend too much time on it, trying to do them by hand. Finding the total area of the rectangles. Well, we got 4 of them. Rectangles are just length times width. We know earlier the width is going to be a quarter, or 0.25. The only thing that remains there is to figure out the lengths of each of the individual rectangles that are on the page. And then, yeah, just add them all up.
Is it like 0.46875?
Potentially. Let me just quickly change this fraction. 0.46875, yeah. Yeah, that's fine. Again, that's a closed form decimal, so that is fine. It's not particularly typical to use decimals for those. Usually you see fractions as the answer, but it is, yeah, as I said, totally fine, as long as it's a closed decimal. Typically speaking, if you were to do it by hand, it would just be, your length times width of each of these. Getting the lengths was just a matter of subbing in the corresponding x-coordinate into the function, because you can see that the function, all these rectangles have their heights associated with the curve on that graph there. So at each of these points, 0.25, 0.5, 0.75, you can get your y value and thus the length from there. Part C, find the area between the graph of the quadratic, the x-axis, and a line x equals 1.
Chris, is it 1 on 3 units squared?
It is 1 and 3, yeah. How'd you come to that conclusion? What's the overall approach for that?
I didn't use my CAS for this. I just integrated x squared, which is
Mm.
x to the power of 3 on 3.
Yep.
And then you sub in 1 and you minus what you get after subbing in 0.
Yeah, yeah, correct. So you do your antidiff, which gets you to, well, I haven't written it here, but yeah, capital F of x is going to get you to x cubed on 3. Then you do capital F of 1 minus capital F of 0. Yeah, that's going to get you to a third. Nice and easy. Um, I guess a couple of things to get both marks to that. One would be doing the integral itself, and the other would be the answer. It's a bit tricky to somehow squeeze 2 marks out of that, but yeah, those are those would be the main things to be looking for there. Okay, next up, part D, the graph of, hang on a minute, graph of f. Oh, okay, it's just a new function. Yeah, graph of f, it's a bit wonky, but I guess that's deliberate so that they can make sure the graph is intersecting some known grid lines to really help out a bit. We're going to approximate the integral shown using 4 rectangles and aligning the right endpoint of the rectangle with the curve. So basically, when you draw your rectangles, the point at which the rectangles intersect the curve should be on the right-hand side corner, not the left-hand side one. Um, I'm debating whether or not to show you a picture of it because part of the challenge of this is setting up those rectangles, because if you do it in a different way, you get a different answer. Um, this will be, actually no, this works, yeah. This is right endpoint. You can see the right hand side of the corner of each of the rectangles is touching the curve, whereas the left hand side is sort of just hovering there. That's what you want to have happen here, right endpoint.
Is it going to be -8?
-8's a bit big. Um, Maybe double check the math on those, and if that's fine, we'll have a look at the picture and see if you got the right rectangles.
Is it -2?
-2 is better. Yeah. Was that a arithmetic thing or was it a rectangle thing?
Yeah, the last rectangle I accidentally multiplied 6 by 2 instead of 6 by 1.
Hmm. Sure. Okay. Um, yeah. As far as how you would go about that, I've got the rectangles depicted here. Yeah, that's about it. Nice. And for that one, like all you're doing is reading off of the grid lines. Yeah, so you can see that's going to be the 6, that's going to be the 2. There's a -4, there's a -6. You can just sort of read those off of the grid lines. If you didn't have grid lines, but you did have the rule of the function, you would basically be doing a repeat of this one, essentially. We got x squared and root x. Find the area of the shaded region. Fairly standard question. Bit of a funny answer.
Is this 1 on 3?
It is also 1 and 3, yeah, just like we had from before. So in this case, what we're looking to do is a top take bottom scenario. A couple of ways you could have done this. Because it's CAS, you can pretty easily just say, yep, root x is the top curve, x squared is the bottom, and they cross over at x equals 1. I can very much just chuck that into CAS and be fine. This might be a bit of a pain to anti-diff by hand, not the end of the world. The other way you could have done it is noticing that these are in inverse pair. So if you're doing it by hand, you might want to favor using the line y equals x as your top function and then just doubling it. So using y equals x would give you like this bottom half of the area, and then doubling that up is potentially another way of doing that. So you don't have a power of 3/2 in your handwriting. But yep, always top take bottom for bound area. Here's where it's going to get more interesting. Quadratic is being transformed by multiplying by a between 0 and 2. Find the values of a such that the area defined by... So basically this quadratic is now going to be ax squared. We still have this same sort of bound area. We want to figure out, okay, we're toggling a between 0 and 2. A is going to be the upper bound as far as the domain is concerned of the bound area. We want to figure out what values of a are going to give a bound area of 1/3. 2 decimal places. Or marks. It's a tricky question. I would highly recommend plotting both on the CAS and then observing through a slider what's going on as you toggle a between all the values that are there. Okay. So I'd set something up like this. One of the other things I'd probably want to do is put in the line x equals a. That way, when I toggle a through all the possible values, everything should now change. So you can see, well, even just starting at a equals 1, right? That's a fairly obvious starting point, because when you have a equals 1, you literally have the exact same scenario we started with in part E, x squared. And we already knew that gave the area equal to 1/3. So right off the bat, we've at least got something down. We've got if a equals 1, the area is going to be 1/3. That's really good to know. The challenge now is going to be getting the other values out of it. So we can see if we increase a, to its maximum of 2, we can see that the cutoff point for our bound area is going to occur much later than it did before. And so when you're doing a bound area, you need to have both this and this. You need to have 2 separate sections. Whereas as a gets closer to 0, we can't actually make it equal 0, because otherwise there would be no line anymore, and that's just not part of our domain. You can see that we only really have one section of area to worry about, which is just whatever's in the middle here. So this is a kind of question where, as you play around with A, you'll notice there's actually 2 distinct possibilities when it comes to getting your area equal to a third. And you'll have to have separate ways of going about it, depending on what you have. One of those scenarios is significantly easier to try and solve for, so I'd recommend solving for the easier one first. Which, by the way, would be this one. Right? When your x equals a is to the left of the crossover point, you don't have to have a second integral for your top take bottom scenario. You've just always got top take bottom with one scenario, one function. One function is above the other for the entire duration. But as soon as your a gets greater than 1, suddenly you now have 2 to worry about. Like so. Any a greater than 1 is going to achieve this. One area up here, one area down here. Any progress being made so far? Anyone got an idea of something to share, whether it's the answer or just something you can do to get closer? Shall I maybe just jump in then and explain it start to finish? Who's still trying to do it themselves? I don't want to steal it from you if you're doing it. Nothing? Cool. Okay. Let's see. So, as I discussed, there's pretty much 2 main circumstances. One where if your a is greater than 1, you're going to have a crossover of curves. If your a is less than 1, then you're no longer going to have that crossover happening anymore. And so that gives us the 2 scenarios we need to solve for. The first scenario is very easy, because if you just have no crossover, then you're always cutting off at a, whatever a is equal to. So for the scenario where a is between 0 and 1, you're always going to cut your integral off at a. You're just doing a top take bottom of a. And on the CAS, you're literally typing this in exactly with a CAS solve. CAS solve for 0 to a of root x. You don't really need a separate integral. You can just have the x squared in there like we did here. There's nothing really different there. And then yeah, that's just going to give you your 2 values. A equals 1 makes a lot of sense from before, and a being 0.77, well, If you wanted to, you could sub that back in and prove it, but that does take a bit of time if you want to do that. Now, when we're doing a greater than 1 up until 2, we now have to worry about the crossover point. So the first thing we want to do is figure out where would they cross over. And so I've chosen to do an inequality here. You don't really even have to bother. You could just put where does ax squared equal root x. Now that'll just put an equal sign here instead. Point being, we just want to know where do they cross over at. We still know, because that's the main part that really matters, because we still know the final integral bound is going to end at a, because it has to end at a. It's more so where do I then split and do the flip. So the first half of it, so if we maybe even have a look at the CAS on the document camera, like this crossover point here would be a to the power of negative 213, where in this case a is 1.5, I guess. That first integral will be solving this bit, where you've got the square root on top of the quadratic. Then the second bit, again, it's going to end at a, because it always has to fully end at a. And once again, we're going to equate that equal to a third, because we're trying to find what values of a would give us a bound area of a third. So in total, a equals 1, a equals 0.77, a equals 1.13. Doubling up on a equals 1 is a bit of a good sign, because if you're looking either side of a equals 1, but including that spot, it's a good sign that you've done something right when you're actually getting that same solution more than once. Yeah, that's overall the way to go about that one. 4 marks in total, so fairly involved. I'm curious what the 2% got 4 marks. 2% of people who did this exam got 4 marks in total. Nice. Although to be fair, 42% got at least a mark. I would imagine that was the people who said a equals 1. So there was a reasonable chance of getting at least a mark on this question, but there was a very sharp drop off on how well people did with this. That was fairly involved. Is there anything else I should discuss about that to clarify things? Okay. Next up, question 3 then. Much easier questions. State the maximal domain and range of Q. Doing that thing again, isn't it? Where whenever I click over, I'm even seeing it on the screen share, whenever I hover over a thing, it puts up this little box. Damn. Oh well, I shall avoid that where possible. It does it intermittently. Hmm. Oh, now it's just flat out gone altogether. Great. That might have fixed it. Can you guys still see the screen share? I think it should be fine. Sweet. I mean, either way, you've got a copy of it, of course. So you're probably better off using your own copy of things. But yeah. But okay, maximal domain. So Keyword maximal domain essentially just means what are all the possible x values that can be put into this function. So what you now have to consider is what kinds of x values can't fit into this. What reasons are there where an x value cannot exist in a graph? For logarithms, there's a very specific reason for where certain x values are not allowed. So think about when you're graphing just a regular logarithm, there's a certain domain of values you don't draw when you graph it. You can potentially use that to figure out what the restrictions are for logarithms. Um, range is a bit trickier because you've got two separate things you're keeping track of, two separate logarithms. There's a way to simplify things though. The maximal domain part is probably the easier part. Range is a bit more challenging. Oh, go
Chris,
ahead.
is the maximal domain with the curl, no, not the the rounded brackets,
Mhm.
negative infinity to -1?
Sure is. Yeah. How do you go about that?
Well, first I put into the graphing tool, but anyways, like if you do sub in anything like anything more than what's it called -1, I think like the logarithm just breaks down.
Yeah. So to oh, okay. So you're looking at this specific scenario, yeah. So I guess globally speaking, logarithms can never have a zero or a negative in their brackets as the final result. And so yeah, having anything greater than -1 in this case would cause that um, for at least one of those. And so yeah, the way I've sorted it out was pretty much you look at the brackets of each of the logs, and you force them to be greater than zero. Then you just do the intersection of the two things, and that's going to get you negative infinity to -1. So that's domain. Did you have a thing for range as well?
I'm not really sure about range.
Okay.
I know it will definitely go to negative infinity to the for the bottom end, I think.
Yeah, well, it definitely goes to negative infinity. You're right. Having that,
Uh,
having it on the graphing tool was a good idea. Yeah,
yeah.
it's one thing I didn't actually really consider when I was suggesting an idea of how you could simplify things. Because yeah, you could just look and see what's going on with the graph. So are you saying that it's not super clear what's happening at the top end?
No, I can look a little closer to figure out, but I'll see.
Hmm. Yeah. Okay. Um, there's other things you can do beyond relying on the graphing tool. If you can see it's trending upwards, then what you can do is you can do like a limit on the CAS. You can sub in a really big x value. You can sub in infinity. There's things you can do on the calculator tool to try and get an idea of what's going on there. And I'm pretty sure the CAS has a range function. Well, I know at the very least it has a domain function. Maybe it has a range. No, no range. Well, yes, it has fmax. Fmax will be fine. Fmax and fmin, I suppose, is your range function. You just do fmax fmin over the full domain, and Yeah, that's a way to hack it. I like that actually. I just sort of came up with that now. Yeah. Oh no, it doesn't work. Kinda. Got a control enter it. Okay. So if you're subbing them in directly, you're getting undefined in those scenarios. Next best thing you can do is a limit. So as x approaches -1, still undefined. So for this one as well. Okay, that's a bit better. Um, yeah, we kind of already knew it was happening at the -1 range. It was shooting all the way down to negative infinity. If you look at what happens as it gets closer to negative infinity, the y values increase forever. I don't know if it's done it. Maybe it has. Nah, it hasn't. You could use the quotient law of the logarithm to condense it down to a single logarithm, and then realize that as the brackets of the logarithm get bigger, the y value should always get bigger. Natural log will default to having a range of real unless it's restricted in some sort of way. And in this case, part of the restriction was its asymptote, so it's going to have that full range of all real numbers. Let me see what was actually going on the graph. Yeah, okay, so it just looks like a logarithm. That's fine then. Yeah, doing something like, basically it end up being x squared take 1 over 1 take x. And as long as you're seeing that when I shove in a negative x value, the net result is a bigger positive every single time as I get more and more negative, that trend line will always shoot to infinity. Anything to clarify there? Um, Actually, maybe one other thing would be the domain. So, pretty sure there's a domain function. Yeah, there you go. Domain h of x, comma x, and you just it's just there. It'll just do that for you. I don't know if the Casio has that or not. Probably not. If I were to take a stab, I'll have a browse just now. I haven't looked, but yeah. In the meantime, part BI, the equation of the tangent at x equals -2. did exist, I would have found it. But if you look at the catalog, or at the very least, it's not called domain. So otherwise, it would have been around there-ish. Okay, this one definitely exists on both CASs. There's a thing you can immediately do with. There's nothing you actually have to find. You actually have all the key information necessary to just plug directly into the CAS for this one. The CAS has a function for finding tangent lines.
Chris, is it y is equal to -3 on 2x minus 3?
Y is equal to -3 on 2x plus 3.
Minus 3.
Looks a bit off there. I wonder what function you put it into. Did you do it by hand or by CAS?
Try to do it by CAS, and I got that, but then -x minus 2, but then I kind of doubted myself, and then I tried
Oh,
to do yeah.
oh, okay, interesting. So when in doubt, plot q of x, plot the tangent, see if it's tangent, because you do have CAS. You can very quickly check that. In fact, since you already have q of x on there, literally all you have to do is grab that negative x take two, and you don't even have to copy paste it. It's pretty easy to belt that out on the entry. But yeah, so for Casio, it's this one, the tan line. For TI Inspire, it's down here, tangent line. Both of those have that. Uh, by the way, all the syntax in these exam solutions is TI Inspire. Where there's a major difference, I'll mention it, but I'm pretty sure the syntaxes are very similar between the CASs. Okay, that's that one. Up, I, perpendicular at the same spot, but it's also got to pass through the point -2, 0. That's weird. I don't think that even matters. The whole passes through -2, 0. Why would that matter? I guess we'll find out. Yeah, I don't know. That seems just like redundant information. I just noticed my Casio has decided to resurrect itself because for a while it was on 1 bar, and for whatever reason today it's decided it wants to be on 2 bars.
Is it y is equal to x plus 2?
Yeah, y is equal to x plus 2. Normal line function exists on both. Syntax, again, is going to be very similar, borderline identical to what you would have done before. The fact that it passes through the point -2, 0, I don't really know why that's there. You, in fact, they've actually repeated the same thing because you're taking the perpendicular line at x equals -2, and they've repeated that in the point. Bit weird. I guess they've just given you the y value if you wanted to do it by hand. Maybe that's why that's there. How hard would it have been? -2 into that, -2 into that. Yeah, I don't know. Anyway, same thing as last time. New function, p of x. Why is it not 1-to-1? It's going to test your understanding of definitions. This will never be an issue in a real exam because you'll have a bound reference that you can look up definitions in. And so really all you got to do is look up your definition and be like, yep, it's not that. Got it. One-to-one function is defined as follows, does not meet criteria. So who wants to take a stab at describing why?
It also doesn't pass the horizontal line test.
Yeah, it doesn't pass the horizontal line test. Remind me what that is again.
Like if you were to draw a horizontal line anywhere on the graph, it should only have one intersection.
Yeah, correct. For it to be 1-to-1. That's probably the most succinct way of putting it. P does not pass the horizontal line test. In my solutions, I've done a more mathy speak. P is not a 1-to-1 function because not every unique value of x maps to a unique value of y. That's the kind of language they put in the textbook, so I've just sort of repeated that there. I don't think there's anything wrong with saying horizontal line test. Let me have a look in the exam report. Oh yeah, that's totally fine. So accepted answers were fails the horizontal line test, many-to-one function, there exist two x values for some y values. Yeah, they didn't really seem to care too much. Apparently, God, imagine being the student that said many-to-one function as their response to that. That feels borderline on the edge of being a bit suspicious. Explaining that it's not 1-to-1 simply by saying it's many-to-one. So yeah, the wording didn't seem to matter too much for that. That being said, it was still a fairly low pass rate question. 66% of people got the mark. Anyway, part D, much more straightforward. Find the gradient of the tangent at x equals a. Slightly more challenging, I guess, than what you might see in a textbook. Only slightly. Gradient of tangent. That is a keyword that shows up, or I guess a key phrase that shows up a lot in the textbook. In fact, I believe it shows up through the entire differentiation section every single time they introduce a new diff. There's always, like as in, here's your x squared diff, here's your e to the x diff, here's your whatever diff. There's always a question in there that says find the gradient of the tangent. Now, normally they have it at x equals 2, or x equals 4, or whatever. This is x equals a. Shouldn't really change much. You just, instead of putting in a 2 or a 4, you're putting in an A. Um, you can cas it out quite quickly as well. Gradient of tangent.
Is it 2e to the power of negative a minus 2e to the power of negative 2a?
A to the power of A minus 2e to the power. Yeah, yep, that'll be good. Nice. Um, I've decided to go the full tilt, find the tangent line, and then just steal the coefficient off of the x term. It's only slightly faster than doing p dash of a. The reason why I've decided to do it this way in the notes is because the slightly faster aspect comes from the fact that usually when they ask these kinds of questions, having the tangent line equation just in general is nice. Um, and this gives you both, obviously, because it's a linear. The coefficient of the tangent line is going to be the gradient. The coefficient of the x, sorry, is going to be the gradient. So I've done it that way, or you could just do p dash of a, right? You just get the cas to do a diff on that, and then you sub in x equals a into whatever came out. It's going to give you this. This is a factorized form. You can fully expand. It's totally fine. Oh god, I remember this question. Good luck. It, yeah, do your best. It's a tough one. A lot of trig going on, similar angles and such. You've got a linear, um, and the tangent to p at x equals a. So, reminder of that, we've already figured out what the tangent of p is at x equals a. That was that full nasty equation. And so basically you're taking some tangent line off of p, and when you do so, it is intersecting this y equals x plus 2 at some certain angle. Now, you want to get the acute angle that is between the two. So obviously if I draw a straight line anywhere off of this graph, you're going to have a pair of acute angles and a pair of obtuse angles. And beyond that, not only do you have to find the acute angle, but you're actually forcing the acute angle to be 60 degrees. So when you're playing with where you could potentially take tangent lines, when you identify where the acute angle is, you can then sub in 60 as its value, and then solve from there. Because the goal is to effectively say, find the value of A. If you walk it back, the value of A is just what x value am I taking my tangent at. You can play with this on the cas a little bit. You can go back and grab this tangent line equation, define it as some f of x whatever, and slider your way through all the possible values. Now, you're not really given a domain here, but you can have a reasonable assumption as to what you probably should do to make it happen. Yeah. I'll give you a moment to play with that for a bit. This is very much one of those questions where you have to sort of work with the CAS on it. If anyone has any sort of conclusions or anything to bring up, I'm more than happy to go through those things, but I'm expecting it might just be I'll go through it from top to bottom. But we'll see. Probably don't have an answer, but is anyone coming up with any sort of conclusions or insights as to, after having played with the value of A, is there anything worth discussing? Cool. Yeah, it's a tough one. Let's see. Pass rate. So 83% of people got 0 for this, which is honestly lower than I thought. I would have thought this would be a really tough question for a lot of people. Still was tough, absolutely, but not like didn't floor everyone, I guess. Cool. There's a lot of shit going on here. I've got a few pictures just to sort of highlight it. Basically, this red line, this straight red line that I've drawn, is just a place at which you could take a tangent off of the function. And so, under certain circumstances, if you take the tangent from below, one possible scenario might look a bit like this. If you took it directly at that intersection point, it might look something like this. So note that, I guess in this circumstance here, you're going to have the obtuse angles here and here, and you're going to have the acute angles here and here. And so part of the understanding of the question is going to be, hey, which one's obtuse, which one's acute? Like in this case here, if you take it right here, you've now got the acute angle down here as opposed to in here. All right, so where it's located in the, you can kind of think of it as quadrants, from there, or there, depends on where you take this tangent line at. And so that's part of the understanding of the question. Now, what do I actually need to do from here to solve something? A few things that are worth pointing out. Because we're working with angles, I want to basically chuck as many angles into this thing that I can know as possible. One of which is the gradient of the linear x plus 2 is going to be 1. That means that you've got 45 degrees for that particular angle. So, you've got 45 degrees here, it means you also have 45 degrees here. The similar angle thing if you were to draw your parallel line to the x-axis. And so, if you know this is 45, and you know the whole acute angle is 60, then we need to figure out whatever this missing angle is, because that'll relate it back to the angle of the tangent line that we're trying to take. You can see how if you take a tangent line, it's going to have some angle. I've used the Greek letter phi for that. That angle is reflected in here through similar angles. I don't really know the terminology, by the way. I'm just going to call them all similar angles. I'm sure there's some specific property how it does this little flippy flip. But point being, this flips into that. And so, you know, this is 45, this is 60. We now know what this angle is. And because gradient is associated with angle, That's going to give us the gradient that this tangent line must have for it to create an acute angle of 60 degrees. Tough stuff. So if we have a look at that, right, there's that 60 minus 45, you've got 10 and 15. And you're basically equating that to the gradient, right? So 10 of 15 being the gradient of the function. The gradient is also given by f dash. And so since you can equate those two things together, the only thing left is a as an unknown. That's going to give you one of these answers. The other is going to come from this scenario where the acute angle is on the bottom. So again, we've got to try and do some angle arithmetic to try and figure out how we're going to get this angle. So again, we're going to take copies of this 45. Draw your horizontal off of the point of intersection, kind of like how we had it here. So you can start reflecting and using similar angles. The thing I chose to use in this circumstance is that any angles off of a straight line have to add up to 180. So like this 60 plus this is a total of 180. Look, when it comes to this sort of stuff, there's a lot of ways you could do it. I imagine this isn't the only way, but this is just what I did. And so yeah, you got 60 plus this plus that equals 180. Again, that's just another thing you can very quickly solve. That's going to get you 75 degrees that were left over. And then you equate that to gradient to once again get the other a value. So yeah, a lot of pain there. Most students got nothing. Some students might have probably did this one, I imagine, which was you just take a tangent somewhere, do some angle math and be like, oh yeah, I found one, nice. And then you just don't look any further. And the marking distribution sort of shows that, which is if 83% of people didn't get a mark, the remaining was split as 4% on 1 mark, 2% on 9% on 2 marks, and 4% on 3 marks. That's a weird little distribution, actually. More people got 2 marks than got 1 and 3 marks together. That's interesting. I guess it depends on where the marks were distributed in that particular question. Like, for instance, if you got the first mark, most people would know where to go from that. Once they got the first mark, of course, which is a tough sell. Dare I ask if anything needs clarification there? Probably does. Happy to explain. Anything in there you want me to go over again? Cool. Okay, we are getting close to end of lesson, so what I'll do is I'll just sort of quickly breeze through F. Find the x-coordinate of the point of intersection between x plus 2 and the graph of P. So that's really easy. P equals that. Hence find the area bound by y equals x plus 2, the graph of P and the x-axis. So x plus 2, P and the x-axis. You're looking for this little thing, triangle looking thing in the middle, which would be that. Not a whole lot really going on there. It's a pretty simple bound area thing. Now, the interesting part about this is even though it mentioned 2 separate curves, it's closer to a crossover of curves type situation than it is bound between 2 curves, because neither one of these is on top of the other. You've got the linear, which is on top of the x-axis for the entire duration, and then over this crossover point you've got p of x, which is also on top of the x-axis for that entire duration. And so rather than doing like a y take p type situation, you've actually just got the x-axis as your floor for the entire duration of the domain. And so it ends up being simpler than it would have otherwise been. You just got to figure out what this crossover is and cut your integral accordingly. But as we said, that's really, really easy. just make the two functions equal to each other like you always would, and then cas solve. And then yeah, give to however many decimal places they wanted. That's about it. If there's anything further to clarify, please let me know. Otherwise, I'll let you enjoy the rest of your day.